Hello everyone. Today we're going to talk about the Booth's algorithm, and we're going to do binary multiplication using this algorithm. This is going to be a quick explanation of the operations. I'm not going to dive deep into how it works, but this is going to be valuable. So let's think about what we need to do. So first, we need to write down three values when we're trying to do these operations. The first value is just a multiplicand, which is, let's say you want to do, 2 times 3. The multiplicand would be 2, and the multiplier would be 3 in this case. So this would be 2, this would be 3. And 2's complement of m. We denote that by either negative m or m bar. All right, so let's, so three values, m, q, which is the multiplier, and m bar, or 2's complement of m. All right, let's go down. So for these calculations, we need three different registers. An accumulator, I'm going to use 5 bits for the accumulator and the multiplier. So we need an accumulator and a multiplier register, which we're going to call Q. We also need 1-bit register for Q minus 1. We're going to talk about what that means, but this is all we need. We need 3 registers, 2 5-bit registers, and 1 single-bit register. The final result is going to be stored in the accumulator and the multiplier, the Q register, and it's going to be read in this order from the accumulator to the Q register. Now, there are 4 types of operations that we need to do, and those operations rely on the rightmost bit of Q and Q minus 1. Now, this is we can denote this rightmost bit of Q as Q0, because that is basically the index 0, and this is Q minus 1 sub minus 1 because that is the negative 1 index. You could think of it as that. So there are 4 types of operations. We could have 0 and 0 for basically 0 for Q0 and 0 for Q minus 1. So that would be 0 here, 0 here. Or we can have 0, 1, 1, 0, or 1, 1. So something to keep in mind, something to realize is that when we have 0 and 0, this is the same if we also had 1 and 1. Both of these are going to just do the same operation for us. So we're going to do an arithmetic right shift for both of these values. So if we have 0 and 0, or if we have 1 and 1, it doesn't matter. We're going to do arithmetic right shift in both of those cases. That's the only thing we're going to do. And for the other cases, when we have, over here, we have a 0 and 1, so that is the 0th index is 0, and the negative 1 index is 1. That is going to be, we're going to say the accumulator is equal to value in the accumulator plus m. And after that, we also need to do arithmetic right shift. This is important. With every type of operation, we have 4 type of operations, right? We have this one, this, and this. For every one of those, we are going to do an arithmetic right shift, regardless of what we do prior to that. In the end, we're going to do an arithmetic right shift. All right, so 0, 1, that indicates accumulator equals a plus m. If it is 1, 0, that means accumulator equals to a plus 2's complement of m, which is pretty much a trick used to say a minus m. That is, that's how they do it. When you want to subtract a value, you just say, let's add the 2's complement of that value. That is the trick that's used, and pretty much that's pretty much it. Let's do an example. So let's say we are doing 6 times 7. Let's write down everything that we need M is the multiplier. Off to the side, I'm going to write these down. 1, 2, 4, 8, 16. I'm going to say how to get 6. That would be 1, 1. These are all zeros. So 6 is going to be 0, 0, 1, 1, 0. And for the 2's complement of M is going to be basically flip everything. 1, 1, 0, 0, 1, and add 1 to it. And now we add 1 to it. When we add 1 to this, what's going to happen is this is going to turn into a 0. This is going to become a 1. So let's do that adjustment. 0. And that is it. So let's now write down what our Q is going to be. Our Q, I'm going to write it in a different color. Q is going to be, so that's 7, right? Which would be just 6 plus 1. In that case, that's 7. This is 6 plus 1, that is 7. All right, beautiful. Now we're going to write down the registers. I'm going to make a chart. So this is the accumulator, this is Q, this is Q minus 1. And, all right, beautiful. I'm going to make this, move this a little here, and I'm going to say this is the operations we're going to perform. So the very first operation is the initialization. So we're just going to put everything in their place to start out with the operations. The accumulator is going to start out with all zeros. The Q is going to take on the value of our Q that we have, and Q minus 1 is 0. All right, beautiful. So what is the first operation that we're going to do? Okay, let's look at these values. This is the 0th index of Q, and this is the -1 index of Q. We always initialize it as 0 when we start out. So what we have now is the combination of 1 and 0. We go back to our chart. 1 and 0 says A plus the 2's complement of M right here. So let's go and do that. So when we do that, what happens here? What happens is that the accumulator just gets the value of the 2's complement of M, because it is all zeros at the moment. All right, beautiful. Everything else is going to copy over. And we're going to write down what we did. So we said A plus 2's complement of M. And now let's remember, with every single operation, we're going to end it with an arithmetic right shift. So we need to do that now. Also, something important to remember, when we do an arithmetic right shift, we're going to copy the most significant bit. So let's say we have 1, 1, 0, 0, 0. When we do an arithmetic right shift, that's going to be 1, 1, 1, 0, 0, 0. So the best bit, that's basically what you do. You copy the most significant bit to the new space that we've acquired. So that's arithmetic right shift. A logical right shift wouldn't do this, but arithmetic right shift certainly does. That's something to keep in mind. So now let's do that. That will be 1, 1, 1, 0, 1, 0, 0, 0, 1, 1. And we move the other bit, the 0th index, to the Q minus 1, right? We moved this guy over here, and that is basically what you do with every arithmetic right shift. You move the guy into it. Notice that with the initialization, we didn't do anything else. We just said let's initialize, but now since we're doing an operation already, we're going to do the arithmetic right shift. All right, so we did the arithmetic right shift. We indicated that we did it. We have, all right, everything's cool. Now let's think about what we have. We have 1 and 1. Let's remember, when it is 1 and 1 or 0 and 0, that is going to be essentially just an arithmetic right shift. So what we're going to do is we're going to say no operation for the, basically we're saying no subtraction or addition has been done. So we just copy it over and we indicate that nothing has changed in that regard, but we need to do an arithmetic right shift, so we do that. And the easy way to actually do these is just to say that, oh, this is moving over here, this is moving here, and you just do that until you run out of values to move over. So it's just easy to think about them as diagonal movements. And we say arithmetic right shift. And one more thing to keep in mind is, how do you know to stop? How many times are we going to do these operations? Well, we're going to do it n times, where n is the number of digits for q, or multiplier, right? That's that many times we're going to do it. So we have 5 digits, 5 bits, so we're going to do it 5 times, and we'll be done. All right, so let's see. So we have 1, 1 again, so we're going to do the same thing. I'm going to copy all of these, put this here. I'm going to say no operation, because we didn't do addition or subtraction. But we're going to do the arithmetic right shift. Am I doing this correctly? Because I'm doing it fast and I don't want to mess it up. All right, beautiful. And this was an arithmetic right shift. All right, next up, let's see, what are we doing? Yeah, so we have 0 and 1, 0 and 1. So this is the Q0 index. This is the Q minus 1 index. We go up. So 0 and 1 tells us to say a plus m. Basically, a plus the regular m multiplicand. So we do that. All right, so what would it be? So this is our A, right? This is our current A, which is the accumulator. We're saying that, add that with this, which is the regular multiplicand, right? That is not the 2's complement, but just a regular. We put these together. Off to the side, we're going to do the calculation. Don't do it in the chart. I mean, you can do it, but it just clutters everything, so I don't do that. I'm just going to use a different color. So we have this. Over there, we have a 0. Okay. Yeah, we have a 0. 1 carries over. Just going to move these a little closer to each other so we can see what's going on. So when we added these two, we had 1. When we added these two, we have 0, and we carried 1 over. So when we add these two, we're going to have 0, but let's remember this guy is over here still, so that goes down. But we also need to carry one guy over. These two added, 0, 1 carries, but we still have another 1, so that guy went over there. All right, nice. So this is going to be 0. This is going to be here, 0, 1. Now, this 1 is going to be discarded because we only have 5 bits. So that most bit just is going to be discarded. So that's our value. We are left with 0, 0, 1, 0, 1. That is our value. I'm going to remove this from here. So let's copy over our Q value. And 1 there. Oh, did I make a mistake? Yes, I did. All right, now it is. Good. So we copy over the Q and the Q minus 1 values correctly. We indicate what we've done. We said A plus M. That's regular M. Right, so now we're going to do the arithmetic right shift, which is going to be 0, 0, 0, 1, and then another 0. Let me see. I just need to make sure that I do this correctly, because sometimes I'll make mistakes because I'm not careful. All right, beautiful. And there is going to be a 0 here. So we say arithmetic right shift. With every operation, we're going to end it with an arithmetic right shift. So let's see how many we've done already. So we have 1, 2, 3, 4. So we need to do another one. another operation, and we'll have 5 of them. N operations. N is the size of the multiplier. So we have 0, 0. Remember, for 0, 0, we are just going to do an arithmetic right shift. So let's copy the bits over. We're just copying them over to indicate that we're not going to do any operations. So no, nope, for no operation for the subtraction or addition. But for the arithmetic right shift, we are certainly going to do something. All right. Beautiful. I think I am doing that correctly. Great. So arithmetic right shift. And let's move this here. All right, beautiful. So we have done 5 operations, and it's always a good idea to write them down off to the side so that you don't accidentally do more than you should, which I should have done, but I forgot. 1, 2, 3, 4, 5. Always, every time you do a new operation, just write down the label, the number. Yeah. All right. Cool. So what's the result? The result is basically 0, 0, 0, 1, 0, 1, 0, 1, 0. And basically, what is that? What did we copy over? We copied over all of this, basically the accumulator and the Q register, and we read them from, we first read the accumulator, then we read the Q register. So like that. Now let's try to calculate what that is. It's basically all of this because we can ignore the zeros in front of it. So what is that? That is, let's write these down. 1, 2, 4, 8, 16 and 32, I think. Yeah, so let me actually do this. So 0 for 1. All right, so now that tells us this is 32 plus 8 plus 2, which is going to be 42, right? Yeah, that's it. Pretty much it. You can verify your solution. And what we said, it was 6 times 7. That is indeed 42. And we got that result correctly. I don't have time to do more examples, but I think you should be able to follow that. The only important thing is here is to follow this chart. 4 types of operations, 2 of them very similar, exactly the same actually, just arithmetic right shift. But when you have 0 and 1, you do A plus M. Otherwise, if you have 1 and 0, you do A plus 2's complement of M, which is essentially the trick that's used to say A minus M. When you add the accumulator and the 2's complement of M, that's the same as saying A minus M. Yeah, basically the way that's subtraction is done. Yeah, that's pretty much it. Thank you for watching.